But I'm here, as Or said, to tell you about core collapse supernova, core collapse supernovae, core collapse supernova science, and modeling. And I'm here to really kind of indicate that we are now entering the era, as I'd like to call it, we need to enter the era of precision core collapse supernova modeling. So I know we have a broad astrophysics audience here, and so I'm going to start with with all the building blocks of what goes into a core collapse supernova and core collapse supernova models. I call it my Lego set, and of course the instructions are still being written, so they will follow eventually. But what we have here, and I'm going to focus on neutrino-driven core collapse supernovae, although I will talk about a magnetohydrodynamically driven core collapse supernovae in relation to that later on. And for a neutrino-driven core collapse supernova, which we believe to be the lion's share of core collapse supernovae, we have essentially all of the following ingredients. And before we proceed, we need to march slowly through each piece to sort of understand the importance of each piece and how they all come together in order to make sense of everything else that I'll speak about later. So we have a supernova shock wave here in this first panel. And of course, we know that a massive star at the end of its millions of years of life has an iron core that becomes unstable and collapses on itself. And that collapse proceeds to very high density, at which point there's a rebound and it launches like a spherical piston, a shock wave. And that shock wave is ultimately going to be responsible for disrupting the star in a core collapse supernova explosion. So the fundamental paradigm, the fundamental idea is actually rather simple. But the first numerical simulation of core collapse supernova was conducted in 1966. So we're almost 60 years after the fact, in another couple of years. So, what has the challenge been all this long? Why are we still working on this to try to figure out how this works? Well, the problem is that as the shock wave tries to make its way out of the iron core, material that passes through the shock wave is compressed and heated, and that material is dissociated. The nuclei are broken up into protons and neutrons. And as a result of that, when you break up a nucleus, you lose energy. You put energy in. And for that reason, among one other that I'll mention in a second, the shock wave becomes innervated. And the second thing that happens is that the shock wave eventually passes what we call the electron neutrino sphere. So we're going to be talking about neutrinos in this business. They're center stage. They're produced during stellar core collapse and after core bounce and shock formation. And they become trapped in this flow, given that the densities are so high, which is really quite amazing, since I think about a quadrillion neutrinos are flowing through every square centimeter of your body right now per second, from the sun. Right? So neutrinos are weakly interacting particles. They don't like to interact, but yet under these extremes, they become trapped. We develop trapped seas of neutrinos that will play a major role in this. When the shock wave passes the surface, the electron neutrino sphere surface, beyond which the electron neutrinos produced are free to escape, basically a huge burst of electron neutrinos occurs, carrying a significant amount of energy with it, and the shock wave essentially is done. It just stalls. It doesn't go away. It's a discontinuity in the flow that remains, but it's innervated by nuclear dissociation. And then finally, the final nail in the coffin is when the electron neutrino burst saps it of the remaining energy. So it becomes a stalled supernova shock wave, an accretion shock through which material continues to flow inward from the outer part of the iron core. The core is collapsing, remember. Okay? So what we have here basically what we have is a situation where we have a protoneutron star at the center. So this protoneutron star is formed how? Well, the shock wave doesn't form at R equals 0. It forms part of the way out in the core. So you have an inner unshocked cold core. And then, of course, there's shocked material that accretes onto that will never be ejected. Okay, so you have this protoneutron star has a cold inner core and a hot mantle. And due to the hot mantle, we have basically the production of all three flavors of neutrinos at this point, electron, muon, and tau neutrinos, and their antineutrino partners, not just electron neutrinos. And we're basically radiating, those neutrinos are radiating from the surface of this protoneutron star, which we can call the neutrino sphere, the general neutrino sphere, corresponding to all of the flavors and their antineutrino partners. The neutrinos are radiating to the tune of 10 to the 52 ergs per second. And they're going to radiate on the order of 10 seconds, 10 to the 53 ergs of energy, which at the end of the day is the binding energy of a neutron star. So you start out with gravitational potential energy, you have infall kinetic energy. That infall kinetic energy goes into thermal energy, which is radiated away in neutrinos. And that's essentially the story here, and that's really the central theme, because essentially the accretion of material and the neutrino luminosities are very tightly coupled, very tightly related. You stop the accretion, you basically you stop the fuel to the neutrino luminosities, they fall off exponentially. And that's going to be important in why we have to move away from spherical symmetry to multi-D, as I'll get to in a second. So here you have this stalled supernova shock wave. You have this neutrino bulb radiating neutrinos, and you have the region splits into two pieces, a heating region and a cooling region. You have the weak interactions here of electron neutrinos absorbing on the neutrons liberated from the nuclei to give you a proton and electron, and you have the same weak interaction for the nu bar, the electron antineutrino. And then, of course, you also have the inverse weak interactions. So throughout this region, you have both happening. You have both left to right and right to left weak interactions happening. But it turns out that they have different radial dependencies. And you wind up stratifying this medium into a net cooling layer and a net heating layer. And this radius that separates them in this nice, neat spherical picture, which of course is not quite the reality, the radius that separates them is called the gain radius. So above the gain radius, we can basically deposit energy in the net. And below the gain radius, we lose energy in the net, and this material will eventually cool down and become part of the protoneutron star, which will eventually become our neutron star, or a black hole, as the case may be. So the idea is, which was discovered by Jim Wilson accidentally, one of the pioneers, the grandfathers of supernova theory, back in 1982. It was discovered accidentally because he left his code running when he left for the office, and came back the next day and discovered that the shockwave had been revived on longer timescales than he was used to running. Right, so he would, we would have, as progress happened, the timescale, as we'll discuss, the timescale, a relevant timescale for evolving a supernova explosion has grown considerably, now to several seconds, actually, which is really makes 3D modeling very, very, very expensive and difficult. In any event, he discovered that this electron neutrino and electron antineutrino absorption or shock, post-shock material heating, shock reheating, was able to revive the supernova shock wave and generate a supernova explosion. So this is really, for a neutrino-driven scenario, This is the heart of it, right? This is the essential physics. We form this protoneutron star through gravitational collapse. We have a lot of thermal energy. That thermal energy is emitted in neutrinos, and the electron-flavored neutrinos through charge current interactions are able to reheat, redeposit enough energy behind the shock wave where now the shock becomes dynamical. As you all know, a shock wave will move according to the conditions in front of it and behind it. It's a discontinuity in the flow. And for it to be a dynamical shock, you have to have sufficient energy, pressure, et cetera, behind it. And as a result, when it becomes a dynamical shock, it becomes strong enough to reverse the infall ahead of it, okay, to generate the explosion. And the way this will work is that the shock wave that has been innervated will, in fact, it's been innervated by the release of electron neutrinos, but then electron neutrinos will come back to save the day to redeposit some of that energy back in here to generate the supernova. So Mother Nature is not that unkind, okay? All right, so the problem is that in spherical symmetry, if you have explosion, then you have explosion everywhere, right? You can't have accretion here and explosion here because that breaks spherical symmetry. Well, that means that in spherical symmetry, the second you start to generate an explosion, you cut off the fuel, the accretion that is fueling the neutrino luminosities. And that's a very precarious place to be. And in fact, it doesn't work for most massive stars, at least in the models. It works for very low mass massive stars, kind of a funny name, but on the order of 10 solar masses, but it won't work for a 15 or a 20 or 25 solar mass star. So you have to, at the end of the day, we have to break spherical symmetry so that we can have our cake and eat it too, and have explosion and accretion at the same time. So enter the multidimensional effects into this problem that are going to, they're not primary in the sense they're not generating the energy necessary for the explosion, but they are going to facilitate the explosion. They're going to assist the neutrinos to generate the explosion. The first to note here that's important for multiple respects is that within the protoneutron star, because we have a weakening shock that imparts a smaller and smaller entropy jump to the material coming across it as it dies, as it stalls, we have an entropy gradient, a negative entropy gradient. In addition, because of the electron neutrino burst, the loss of leptons, particularly the loss of electrons due to electron capture to produce the electron neutrinos, which then goes one way when the electron neutrinos escape, we have an electron fraction gradient, the lepton gradient. And so when we have these two gradients, those two gradients can give rise to Ledoux convection. So there are actually more exotic possibilities on longer timescales here, but for the purposes here, this is Ledoux convection. And Ledoux convection has multiple things, helpful nature to it. One, it can dredge neutrinos up to the neutrinosphere faster than they would get there by diffusion and boost the neutrino luminosity, so the bulb, the luminosity of your bulb. And it also affects the overall evolution of the protoneutron star, convective activity within it. So how the protoneutron star evolves in this whole process is central, no pun intended, to this whole mechanism. Then enter neutrino-driven convection. So, I mean, this is convection you will, if you go home and cook tonight and say boil water for pasta, you know all about this. This is Schwarzschild convection that just depends on an entropy gradient. You have a heat source below, you have material above, and you're heating it, via neutrinos, and essentially you're going to boil the material behind the shock wave. I mean, it's kind of funny to think about it. You know, even after working on this problem for decades, every once in a while I pause and think about that. It's almost a joke to think that I'm going to boil a massive star with neutrinos, considering how weakly they interact. But this is the case here. So you're going to deposit, you're going to heat this material from below. You're going to generate convection. So here you see these red, high entropy, expanding, rising plumes. And then you see the cooler, denser, finger-like downflows, okay? And so now you can see the benefit, particularly of this mode of convection, because guess what? We have explosion here, right, in these outflows, and we have accretion at the same time. So we have these accretion funnels that are then will penetrate to the surface of the protoneutron star and continue to fuel the neutrino luminosities while we generate explosion. So by breaking spherical symmetry, we have broken the chains that have kept us, that kept us for decades, in a state of being unsuccessful in generating supernova explosions in our computer models. Okay, so good. So we have this neutrino-driven convection. And now and each time, so this was discovered in 1982. This first came on the scene in supernova modeling in 1992. And now in 2003, about once every decade, we've added a major ingredient to the recipe. In 2003, we discovered that the shock wave is unstable to non-spherical perturbations. So if you take the supernova shock wave and you perturb it spherically, it will basically settle back down to its initial state. But if you poke at it and distort it away from spherical, those asphericities will grow. And this is known as the standing accretion shock instability, or the SASI. And in 2 dimensions, there's one mode. It's a sloshing mode, back and forth, L equal 1, if you will, in the Legendre sense. And in 3D, there's an L equal 1 and a M equal 1 mode, a spiral mode. So there are 2 modes of instability in the SASI, and we'll see both of those operative in the movie version of all of this that I'll show you, so you can see all of this in action. Okay, so the beauty of the SASI is that obviously it has an impact on the shock dynamics. So right off the bat, you know that it's playing a major role. But to tie back to what we just discussed here, look at this schematic, if you will. If I have a sloshing mode and I basically have distorted the spherical shock to something quasi-elliptical, then I've increased the size of the heating region, right? I've increased the size of the heating region in this particular region at this particular time, okay? And so that's one of the ways that the SASI aids in generating explosion, by generating the region in which you can deposit energy in the net sense by neutrinos. So it increases the neutrino energy deposition just by virtue of increasing the volume over which it happens. It also acts obviously hydrodynamically, as does the neutrino-driven convection. Those upward plumes are punching against the shock, so they have a hydrodynamical impact. And one of the things that happens here too is heating depends on the neutrinos. The neutrino flux away from the source falls off as 1 over r squared. And so most of the heating occurs at the base of the heating region, and convection then brings that energy up to the shock wave, where it can do work on the pre-shock material. So you have these instabilities, this neutrino-driven convection and the SASI acting in multiple ways to facilitate shock revival by neutrinos and explosion. Now, one of the things that's hard to picture, I don't really have it pictured here because this is from a 2D simulation, in which case the turbulent cascade goes to large scales and not to small scales. But when you have this convection becomes in 3 dimensions, becomes turbulent. You have shear in the flows, and it becomes turbulent convection. And the turbulent stresses have an isotropic component and anisotropic component. The isotropic component of the turbulent stresses is like a thermal pressure, and the magnitude of it rivals the thermal pressure. So now we have the thermal pressure from neutrino heating. We have the turbulence-induced pressure helping, okay? And in fact, we'll eventually get to magnetic fields. And as I'll discuss, we'll have the magnetic field pressure, isotropic pressure, helping as well. So we're going to basically, by adding additional dimensions and additional physics, we're adding additional contributions to the post-shock pressure. The more pressure you have there, the more you sustain the shock from collapsing, the more you sustain the heating region, and therefore the ability to re-energize the shock to generate an explosion. Okay, so now I'm going to come to, obviously we know we have rotation in these stars. We expect massive stars, most massive stars, to rotate slowly, but nonetheless that rotation should be included, and in some cases we may have rapid rotation. And then finally we have magnetic fields, and we used to think in the past that in order for the magnetic fields to become important, you needed a lot of rotation. We'll talk about that a little bit more later, but if you have a lot of rotation, the rotation rotational energy can go into magnetic field energy through winding and things like that and other mechanisms. But we now know that you can actually have a spherical progenitor with no rotation, although the SASE will always induce differential rotation in the system. You can have a case where you don't have significant rotation, but the turbulence will amplify the magnetic field strengths in the post-shock region. Okay, turbulence will wind up the magnetic field lines and increase the magnetic field strengths to the point where the magnetic pressure, B squared over 8 pi, rivals the thermal pressure and rivals the turbulent pressure. So now you have 3 significant contributions to the pressure behind the shock. So the cavalry has come in, to help the shock essentially maintain its position and then move outward. One of the things I want to emphasize here, because we'll get to this, all of this physics occurs in a general relativistic setting, okay? So this is drawn to scale based on 2 spherically symmetric supernova simulations that we conducted, one in the Newtonian limit and one fully general relativistic. And here you have the stalled supernova shock wave, you have the gain radius, you have the protoneutron star, and then the magnitude of the size of the arrows indicates the magnitude of the infall velocity. Over here you have the general relativistic case, and this is for a 25 solar mass star. So here you see everything is much more compact. So the protoneutron star is more compact, which benefits you. It's hotter. The neutrino luminosities are larger. The RMS energies, the spectra of the neutrinos are harder. So that's 2 checks in the plus column. On the other hand, the heating region is much reduced. The infall velocities are much larger. So as material comes through this, by the way, as material flows through this, if you don't reverse its infall before it hits the net cooling region, it's lost to the explosion. So you don't have an infinite amount of time to heat that material before it then net cools. So if you have a more narrow heating region, you have less region to heat, and then you also have less time to heat because the infall velocities are larger. So the bottom line is the only way to know what wins is to do it. And what the point of this is to just demonstrate to you that anything that's not, any model that's not fully general relativistic is just not realistic. And we're going to get to that in a bit. Okay, let's get to the 800-pound gorilla. So this is a neutrino event. It's a neutrino-driven event. And neutrinos have mean free paths in this event that depend on flavor, electron muon tau, and energy. And low energy neutrinos have mean free paths that are much larger than high energy neutrinos. So much so that the mean free paths for the neutrinos in the system, depending on where you are and what time it is, can be much larger than the scale of the system involved, right? Than the protoneutron star, for example. So they cannot be described as a fluid, except very deep down, where, like all of the other constituents in the problems, the protons, the neutrons, the electrons, the positrons, who interact largely through strong interactions and electromagnetic interactions, whose mean free paths are very short compared to the system, and therefore they become fluid-like. The neutrinos are fluid-like only at the very center, where they are diffusive and fluid-like. And eventually, when you get to the neutrino sphere, as the photosphere of the sun, you're talking about a region beyond which they simply escape. So when you're traversing this spatial domain around the neutrino sphere, you're in the semi-transparent regime. And then as you go farther out spatially, you go to free streaming. So you have diffusion, semi-transparency, and free streaming. And the only way to describe that is through a kinetics approach, right? By solving for the neutrino distribution functions using the Boltzmann equation, okay? So the Boltzmann equation will give you the neutrino distribution as a function of time, spatial location, r, theta, and phi. It'll give you the spectrum, and it'll give you the direction of propagation of your neutrinos. In 3D, you need two angles or one direction cosine and an angle to uniquely specify a direction. So this is a 7-dimensional problem. So this is even on Frontier at the Oak Ridge National Laboratory, one cannot conduct a supernova simulation by where the neutrinos are treated using the full distribution function, the 7-dimensional object, by solving the Boltzmann kinetics equations. One has to make some approximation. Okay, so the next best thing, this is not a problem that you walk away from and come back 50 years later. This is a problem that we've made progress on by being persistent over 50 years. So the next best thing that is done now, the state of the art now, is to solve for angular moments of the neutrino distribution function. So if you take the Boltzmann kinetic equations and you integrate out the neutrino angular information, it can derive a series of moment equations for the energy density and the flux, energy flux. And then, of course, you have higher moments, but we truncate the equations at the level of the second moment. We call this a 2-moment approach, even though there's 3 of these. So really, we're solving for 4 moments. The problem here is that there is a closure prescription that's required, because the equation for the flux involves the next higher moment. And in fact, in a spectral setting where you don't integrate out the energies, it involves the next 2 higher moments. So you have to specify those higher moments in terms of the lower moments, much like you have to specify the pressure in terms of the density, for example, to close the hydrodynamics equations, because you have a gradient of pressure in the hydrodynamics equations, but the pressure is not an evolved quantity. It's derived from the density, which is an evolved quantity. So we would have the higher moments expressed in terms of the lower moments. These are evolved, and that closure is where all of the approximation is. That's the beauty of this treatment, is the approximation's in one place. You can try different closures and understand the impact, but nonetheless, it's an approximation. And ultimately, the 2-moment approach, however sophisticated it is, has to be replaced by a full Boltzmann approach, okay? So having said all that, let's go ahead and see all this in action before we talk about what happens next. Okay, so what you're going to see here before I start it, in the center, you're going to see the supernova explosion occur. It's in 3 dimensions. You don't see anything yet. And you're going to see 3 slices through the 3-dimensional volume, right, in each of the orthogonal planes, just so you can get a deeper look as to what's happening. And what you're going to see is you'll see the boiling, you'll see the shock form, then you'll see the initiation of neutrino-driven convection, the boiling. You will see the SASE appear. And eventually, in this model, magnetic fields and rotation are not included in this model, by the way. This was begun with a spherical progenitor, no rotation, and no magnetic fields. A lot of the models that have really pushed the frontier have been done without rotation magnetic fields, but we will talk about those some more later. But nonetheless, that's what we have here, and it's really fun to watch. At the end of what you're going to find is there are initially many bubbles, smaller scale bubbles, and eventually some of those bubbles merge and you form one large bubble. And when you do that, basically explosion ensues. And that bubble can no longer be broken down anymore hydrodynamically into smaller bubbles. And you'll see as a result how anisotropic the explosion in the end is. So let me go ahead and do that. So here's my supernova shock wave, the surface there. Oh, sorry, there it is. There's the neutrino-driven convection. You can see the SASE coming into play, distorting the shock wave. You'll see the spiraling mode very clearly in a little bit. And we keep zooming out so we can follow the whole evolution. And you see here the formation of a very large bubble here, and you'll see it now in 3D right in here, in which the explosion ultimately occurs. And we used to say silly things like 3D should be more like spherical symmetry than 2D. In axisymmetry, your explosion can only be cigar-shaped because you can't break the axisymmetry. And so we thought, okay, when we go back to 3D, it should look more like a spherical symmetry. And it in a way it does, but it's not really. So that's the macroscopic physics. So I've alluded to the microphysics already, but what's essential in this problem, over the years, this is the set of neutrino-weak interactions written in a condensed form. When it's written out in terms of flavor and antineutrino, it's somewhere between 50 and 100 weak interactions that have to be included in these models. So what's essential in anything we would call realistic to date is that we have the complete set, certainly this set of neutrino-weak interactions. Lately we've discovered that muons can be important as well, so that adds a number of channels. But this weak interaction set has grown over the years, right? As we've discovered that additional channels can have an impact. On top of that, what has changed over the years is the treatment of each of these weak interaction channels. And so what's important in what we would call today's leading models is that all of the weak interactions are included, and they're included with state-of-the-art treatments. You have to have both, okay? In addition to the weak interaction physics, we have the strong interaction physics, right? What's happening here inside the protoneutron star, what's the equation of state? What's the pressure given the density, temperature, and composition of nuclear matter at these densities and neutron richness? So you have the equation of state, and over time, these equations of state have been more and more constrained by nuclear experiment, relativistic heavy ion collisions, astronomical observations of neutron star masses and radii. So more and more and more, we have more and more constraints, And eventually we have this equation of state graveyard of equations of state that used to be used all the time in supernova modeling and not used anymore. Maybe Latimer-Swesty 220 is still being used. It was used in the simulation I just showed you. But eventually we stop using the ones that have been excluded and are left with only a handful that are still not excluded. And in reality, that handful stems from essentially the same equation of state, just with different treatments of the parameterization of the nucleon-nucleon interaction in the relativistic mean field models. If you don't know what all of that means, it's okay. It just means that even though we're left with a handful of equations of state, they're not all that different in the end, okay? That's not a good thing in a way. It is a good thing in a way. And then finally here, when you get out ahead of the shock, you get into, regions that are not in nuclear statistical equilibrium. And when you're in a region of non-NSE, then you need an entire nuclear reaction network in order to understand how your species, your nuclear species, evolved in this hydrodynamic flow. And if you don't include a nuclear reaction, if you do include a nuclear reaction network, the shock trajectory outward is much more optimistic, because if you assume, say, one mean heavy nucleus, as was done for a long time in the past, then you only have a single nucleus to generate pressure, where if you have an ensemble of nuclei, you have many particles to generate pressure. So by virtue of that, you have higher pressure under the same thermodynamic conditions than you would otherwise. If you have higher thermal pressure ahead of the shock, it slows down the ram pressure impinging on the shock, which assists the shock, okay? So the progress to date, so I've now outlined the nature of the problem. Okay, come on. Oh, please, don't stop now. I will have to, let's see. Let me try this, there we go. So the progress to date, so I've been doing this for a long time, and it was very depressing for a long time because nobody was obtaining explosions right across supernova groups. Jim Wilson was obtaining explosions, but Jim was, we were all doing spherically symmetric modeling just because the computers weren't there and also the know-how wasn't there. But Jim was putting in the convection inside the protoneutron star to which I referred earlier. And he was using a mixing link theory to be able to include that effect in a spherical model. So technically that wasn't really a spherical model. If you take that, what he called neutron finger instability out of the picture, he didn't get explosion either. So nobody was getting explosions in 1D. Because in spherical symmetry, because of basically what I told you earlier, it's like you're trying to play the game and somebody's pulling the rug out from under you. So long story short, fast forward multiple decades now, the efficacy of neutrino shock reheating to generate core collapse supernova explosions has been demonstrated by all leading groups across progenitors of different progenitor characteristics: mass, metallicity, rotation. Okay, so this is good. This is huge progress. We have never had such consensus in the supernova modeling community across models, across different groups. So this is, to say that this is progress would be an understatement. And what I've given you here, and I'll make my slides available, I've listed reviews from each of these groups so that you can hear this from different people and different perspectives. Okay, but as I'm about to describe, demonstrate, the level of sophistication in the models across the different groups varies, okay? And in general is not sufficient. to do ultimately what we need to do, which I'll talk about in a second. The level of approximation in the macroscopic physics, for example, in neutrino transport, it varies. The level of approximation in the microscopic physics, for example, in how many of the neutrino weak interactions are included. And mind you, the cost of a simulation is dictated by the weak interactions with the neutrinos. So the more you have in there and the more sophisticated the treatment of them, the more expensive the 3D simulation is. Hence, it's been the main place where people have gone in and taken entire chunks out or made gross simplifications just in order to be able to run multiple 3D models. There's nothing wrong with that. It all helps. But at the end of the day, you have to recognize that those simplifications are not necessarily going to give you the right answer for that particular progenitor, okay? The numerical resolution in the models has varied from very low resolution to high resolution, and the duration of the simulations has varied. We now know from the multi-D simulations that have been conducted by the multiple groups across the world over the years is that the supernova unfolds over not a half second or 1 second, but 3-4 seconds. The explosion energy still grows in massive progenitors like 25, 30 solar mass progenitor models. It still grows after 4 seconds of evolution. And in a lot of cases to date, the simulations were stopped at below 1 second and conclusions were drawn. Like this model doesn't explode, but it's only been evolved for half a second or 1 second. We now know that you have to run much longer in order to make definitive statements. So some of the mixed outcomes or outcomes, quote unquote, or the mixed conclusions that would be more accurate are based on the fact that we've not carried out the simulations long enough. Yeah.
How sensitive is this to the Neutron-Star's equation of state?
Yeah. So basically, there is sensitivity to the neutron-star equation of state, but the problem is that in the three-dimensional models are so expensive that we do not have a study in 3D where we keep all things equal and we vary the equation of state. We do have studies in 2D which show very dramatic differences in the overall dynamics in the 2D case across equations of state. I can refer, I'm Mez at utk.edu. I can follow up with some references for you on that. So that's part of the problem in 3D is at the end of the day, just pushing the frontier forward, but then eventually having to investigate, when you're in a better place and you've had some success, having to then investigate the sensitivity to certain aspects of the models. It becomes cost prohibitive for now until the future, right? But the bottom line is that question feeds into what I'm about to say. So from my point of view, and that's why I insist on precision core collapse supernova modeling, Mother Nature will hopefully give us since I'm aging, but give us a galactic core collapse supernova before, I'm on the other side of the ground. And when she does, our models need to be, we want our models to be sophisticated enough, precise enough so that our predictions for that given progenitor for explosion energy, explosion outcome, nucleosynthetic yields, whether it leaves a neutron star or black hole behind, et cetera, will be accurate. Okay, and in order to get to that, we will need to elevate the current level of sophistication in the models significantly, as I'm about to demonstrate to you. Okay, but your question pertains to that, right? And then, of course, the problem is, as I said, 3D models are so expensive that people are not so inclined to want to necessarily run the same model you've run so that you can compare, because they'd rather run some other model for some other scientific reason, when it's going to cost them to run one model half of their supercomputer allocation for the entire year. So eventually these things will change when the machines get even better and we can run more 3D models, and people would then be more inclined to do these comparisons. But some of the comparisons have been made, like for example, between ourselves and Max Planck, which are encouraging. Just a closer look, as I was just saying. So here we have two models, one from the Max Planck group and one from our group. 9.6 solar mass progenitor, 0 metallicity, same progenitor, same equation of state, which has now been ruled out, Latimer-Swesty 220. This is not as well resolved as ours. Ours is at 1 degree equivalent resolution in theta and phi, which has been determined to be the minimum resolution needed in order to capture well the turbulent flow in this. But nonetheless, this is not poorly resolved. And they concluded that the explosion, they didn't give a precise number. They didn't run it as far as we did, that it was greater than 0.1 beta, and we determined that it was 0.167 beta, okay? So the Max Planck group and our group, our models are very similar. And so it's encouraging that you have two leading groups among the leading groups whose treatment is similar, but nonetheless has been done by different people with different codes, that we can begin to compare these models in 3D. Okay. Here's an example. This was the first simulation in 3D done at today's sophistication in 2013. The ones that I alluded to earlier were the first two explosion models published in 2015 by Max Planck and our group. This was performed in 2013 with a 27 solar mass star. They were rather ambitious. This is poorly resolved, but they only ran it to 0.4 seconds, okay? And we now know that when you get up to progenitor masses like this, then the determination of whether it explodes or not happens on much longer timescales. So the conclusion here was that there was no explosion, when in reality, it simply could have been a matter of not running the simulation long enough. It certainly was not well enough resolved, which is going to have a problem with regard to the turbulence, because it'll dissipate energy at larger scales than it should, and it will affect the outcome. Over on the right is one of my favorite models by Kuroda. So this model, you can see here two things happening. Number one is he's showing the results from a 20 solar mass star using his code. This is well resolved, that's why I don't indicate that here. And this is the shock trajectory when there's no magnetic fields included, no rotation and no magnetic fields included. And the star, according to Takami, at 400 milliseconds does not explode. But again, in this particular instance, likely he needed to run it significantly longer to determine that. On the other hand, when he included magnetic fields, in both cases, starting with initial field strengths of 10 to the 12 and 10 to the 13 Gauss, which are rather large, he did see explosions. So this is, I wanted to show this as another indication of needing to run the models longer before we can conclude whether there's explosion or failure here. But I also wanted to show it by virtue of the fact that he includes magnetic fields to demonstrate that in this particular case, even in the first 400 milliseconds, magnetic fields have a qualitative impact on the model. So magnetic fields are important. Okay, so progress to date. So basically, I would say that progress to date was achieved through Frankenstein-like models. Okay, this is one of my favorite movies. So what do I mean by that? Well, the way gravity is treated, it's treated with Newtonian self-gravity. And there's an ad hoc correct monopole correction for GR. So you imagine the Newtonian gravitational potential expanded in a multipole series. You take the monopole term and you replace it by something else that comes from the Tolman-Oppenheimer-Volkov equation, which can be expressed as a potential in terms of stuff, okay? So that's the way gravity is treated by us, by Max Planck, by Princeton, et cetera. Kuroda is the only one who is evolving with general relativity. It's one reason his models are my favorite models, not my models. We use Newtonian hydrodynamics, okay? And then, of course, for the neutrino transport, we include essentially with Newtonian hydrodynamics and Newtonian self-gravity with a monopole correction, then the relativistic corrections for redshift are ad hoc. And of course, we handle the transport in the Newtonian limit with special to order V over C. So we do have special relativity built in there, at least to order V over C. But the gravitational redshift is treated in a measure commensurate with this correction to the gravitational field. In addition, we at Max Planck use what's called the ray by ray approximation, where we're solving, instead of one 3D problem, we're solving a set of spherically symmetric problems. And I can go into more detail later as to what impact that has, but that in and of itself is not sufficient. One has to solve a single 3D problem. And as I said, most of the success we've seen has come from simulations without nuclear burning networks, without rotation, without magnetic fields. So just to show you the sensitivity of this is an example that was conducted by Bernard Mueller in the context of a two-dimensional simulation published in 2012, where he ran a fully general relativistic model like we had in 1D. I showed you that comparison. He ran a fully general relativistic model and compared against what we call a pseudo-Newtonian model, which is what I just described to you, where you have a correction to Newtonian gravity, you have Newtonian hydro, you have corrections for redshift and blue shift. And the important point is that in his case, he showed, and this is for a 15 solar mass progenitor, so this is a pretty hefty, massive object. He got an explosion in the fully general relativistic treatment and no explosion in the pseudo-Newtonian treatment. Okay, so this shows the sensitivity of the outcome to the treatment of the macroscopic physics. Then if we go to the sensitivity to the treatment of the microscopic physics, then here we have an example where explosion versus failure is dictated by essentially changing by of order of 15% the coupling constant for the axial vector coupling for neutrino scattering on nucleons. Now, albeit neutrino interactions on nucleons are among the most important in the weak interaction set. So if you know that, if you're going to mess with one of the cross sections, you're going to mess with this one. But nonetheless, I changed the cross section by 16%, and I went from failure to success, if you will. Okay, so this problem has been demonstrated over time and time again, has been demonstrated to be sensitive to detail, sensitive to the precision with which the physics is treated, sensitive to numerical resolution, sensitive to everything. Okay, it's not enough. It's not enough to stop where we are. So what we need going forward, obviously, three-dimensional simulations with general relativistic gravity, general relativistic magnetohydrodynamics, general relativistic Boltzmann neutrino kinetics, a nuclear reaction network, industry standard weak interaction set, and industry standard nuclear equation of state. And to date, there isn't a single simulation that's been conducted with all of this, let alone published. Does not exist. Okay. Not even this exists yet, where we do the two-moment approach rather than Boltzmann. Not even this exists yet. Although Kuroda's work, which I highly recommend reading, I love his models. He's basically done all of this without the nuclear reaction network. Okay, so those are really significant. Those at present represent, in my view, the state of the art in terms of the 3D simulations. So we have a long way to go here. Now, with regard to MHD-driven explosions, in the past, we would naively say, okay, if we don't have a lot of rotation, sorry, I'll use this side. If we don't have a lot of rotation, we have neutrino-driven explosions. And if we do have a lot of rotation, we'll have MHD-driven explosions. Most massive stars are slowly rotating. Some small fraction be rapidly rotating, and that's the story. Okay, well, fortunately now, the progress was initially made through 3D modeling that did not include rotation and magnetic fields, as I said. Okay, the simulations, the models that included rotation and magnetic fields lagged. And now they don't, now we're filling in that space. Okay, and what we're finding, and I cite a number of really wonderful references here, what we're finding is something much more complex, much more nuanced. What we're finding here is that unless the initial magnetic fields are large and the rotation is large and the magnetic field configuration is aligned in a particular way, we're not going to get an MHD-driven explosion. We're going to get a neutrino-driven explosion aided by the magnetic fields. Okay, so now it's not saying that MHD-driven explosions don't happen. They can, but under particular circumstances. So it wasn't as coarsely divided, so to speak, as we did before. Large rotation, small rotation. No, now even with large rotation and large initial magnetic field strengths, if the topology of the magnetic field is not conducive to an MHD-driven explosion, as Boulier, for example, investigated, you don't necessarily get an MHD-driven explosion. Okay, so we're beginning to fill in this space now between the two explosion mechanisms, which in reality may be a spectrum of mechanisms. Okay, so that's the physics, and I don't have that much time left, but I do want to touch very quickly on the numerical. I'm at a center for computational astrophysics. I'm among kindred spirits. I'm among people who have, scars on their backs from doing computation for a long time and dealing with all that's involved. This is, to do this well, in particular to do the neutrino kinetics well, and by well I mean physically faithfully, is a significant challenge. Why? Well, first of all, neutrinos are leptons, and we have lepton number conservation. So we can't just conserve energy, we have to conserve number, lepton number to be specific. If you have to conserve two quantities like number and energy, whose a measure of integration when integrating over the distribution function look like E squared dE versus E cubed dE, good luck trying to find a discretization in a naive way that will conserve both. So this is a very, very difficult challenge, and we have moved away from finite difference and finite volume methods to finite element methods, DG methods. Why? Because the DG methods lend themselves to simultaneous number and energy conservation by virtue of the number of degrees of freedom you have to work with and in particular, the formulation, the weak formulation of DG. That's something that, I can discuss more later, but I couldn't possibly go through that now. So to find discretizations that conserve, I'm pointing to the wrong thing. To find discretizations that can conserve number and energy simultaneously is highly non-trivial, but we're getting there. And we're getting there by considering more sophisticated, higher order methods that have this ability. And this is not just, you can do higher order finite difference, you can do higher order finite volume, but it's the DG scheme that provides this capability. The other thing that we have to worry about is neutrinos are fermions, and they obey Fermi-Dirac statistics. They don't obey Maxwell-Boltzmann statistics or Bose-Einstein statistics. They obey Fermi-Dirac statistics. And that presents a significant challenge to develop methods that will guarantee. So if you're in Fermi-Dirac statistics, that means that the distribution function is bounded between 0 and 1. And the moments of the distribution function in a moment approach are similarly bounded. To develop numerical methods that guarantee, as you move forward time step after time step, that you maintain Fermi-Dirac statistics, that is boundedness of your moments or boundedness of your distribution function, is extremely difficult. We've managed to do it at order 1 to order V over C, and now we're working on the more general case. This is extremely challenging. We document most recently, especially by Paul Lau, my colleague he's an applied mathematician at Oak Ridge National Lab. We've documented some of our suffering in trying to do this. So we have to get real about this business. We can't just generate results and call it science. The bottom line is that if your simulations are not conserving energy and lepton number, then you seriously have to ask yourself, what do you have in the end? I mean, what do they mean? What do the results mean if you're violating fundamental conservation laws? Yeah, Amir.
Just to understand, temperatures during your simulations are much higher than Fermi energy, right? So
the other way around.
The other way around?
The other way around. The chemical potentials are much higher than the temperatures.
I see.
Yeah. So when you are deep in the core, the neutrino distributions are quasi, are Fermi-Dirac-like. They're actually pinched Fermi-Dirac. And the distribution function across angles, for example, is 1. So deep in the core, I can't remember the extent of it, but deep in the core in all of the simulations, the distribution function is 1. You're in a fully degenerate situation. Yeah. So, moving forward, it's fine. We have to continue the current simulations with the current methods, but eventually they have to be replaced by, we have to get serious about developing methods to use to build on which codes are built to use in simulations that satisfy fundamental physics. We have to build that in from the get-go. Because what I can tell you what happens when you violate Fermi-Dirac statistics, this happens in our simulations, and I know it happens in others, but nobody will confess this except over a glass of wine. The code crashes, right? If F goes beyond 1, then you have blocking factors like 1 minus F in the collision term, in the collision integral, and that becomes negative, and all of a sudden emission becomes absorption, and absorption becomes emission, in-scattering becomes out-scattering, and all hell breaks loose. So you go in and you make a little tweak, and then you restart your run and you keep going. And this is what everybody does, whether they admit it or not, right? You nurse your thing through. Well, that has to stop, right? So we can build methods that keep us in Fermi-Dirac space. And I think did I go? Okay, so let me wrap up. This is my last slide. So we have uncertainties, right? We don't have three-dimensional progenitors. We start with spherically symmetric progenitors. So already our initial conditions are limited. So why all the worry about precision modeling if given that, right? Same thing with other uncertainties in the problem or additional physics that may be relevant that we haven't yet, we don't know how to handle yet. I'm happy to talk about all of these in the question and answer period. But my opinion, my approach is we have to basically take the piece that where we know the physics and we have to move toward being able to model that physics accurately as well and build that part of the pipeline, if you will, from progenitor to us and then down the road to whatever happens next. Progress is made by elevating, the pieces in the chain one at a time. And so it's time. We know we've made enough progress. We know a hell of a lot more about core collapse supernova explosion engine than we did years ago. We know the shortcomings in our models and the potential impact. Actually, I've demonstrated the potential impact of those shortcomings on the outcomes. So it's time to get real and time to move on. And I like to liken this to the way, the phenomenologists in philosophy sort of reason, where you bracket the uncertainties and you focus just on what you know in order to make progress. And so we can think of it as a phenomenological approach to this. So on that note, I will thank you for your attention and close and open the floor to questions.
How sensitive are predictions? How sensitive are predictions for the electron fraction to using either the full Boltzmann kinetics or the two-moment kinetics?
So no one has. We have done in spherical symmetry detailed comparisons between Boltzmann and multigroup flux limit diffusion, which is a one-moment closure scheme. We don't have comparisons, for example, in 3D with a model run with full Boltzmann because it's too expensive versus the two-moment. But at some point we will do that. We have to, because if we find that the two-moment closure works well, neutrino mixing aside, I'll talk about that in a second because I didn't get a chance to mention that. If we find that the two-moment closure works well, amen for us, because we could run at the end of the day, we have to run each model for several seconds, and we have to run many models. We have to build up a library of 3D models. And for that to happen, even with current leadership class systems, or even next generation leadership class systems, it's going to be very hard to do that with Boltzmann kinetics. But at some point, whenever you have an approximation, you have to ultimately gauge that approximation against a non-approximate treatment. And that's what we have always been doing, but in 1D and in 2D, but not yet in 3D. So the answer is we don't know yet. And hopefully the answer is favorable, that two-moment captures this. But just to give you an idea, to touch on something I said, the way the closure is done, so when you close the system to relate higher moments to lower moments, the statistics that are assumed are Maxwell-Boltzmann statistics, because it's a lot easier, for technical reasons, it's a lot easier to deal with Maxwell-Boltzmann statistics than Fermi-Dirac statistics. So all of the 3D models are based on closures that are using the wrong physical statistics. And whether or not that matters in the end, again, it has to be done with Fermi-Dirac statistics and then compared. And we don't even, doesn't even exist a method yet to guarantee realizability, as we say, boundedness in the Fermi-Dirac case. That's under development by our group. Now, the other thing is that, I've basically treated the problem completely classically, and that's another way of bracketing. Right now, we know that neutrinos have mass and they mix. And so if you're powering the explosion with electron neutrinos, the mu and tau neutrinos, as you probably know, interact only through neutral weak currents, and therefore they decouple at higher densities, and therefore higher temperatures, and therefore are at higher energies. So if you could mix mu and tau neutrinos into electron-flavored neutrinos, you could boost the heating. There is a mode, there are multiple modes of flavor mixing, and 3 of which are not relevant for the explosion mechanism, but 1 of which it potentially is, known as the fast flavor transformation, fast flavor instability. That happens below the shock, presumably, which means that it could impact shock reheating. But we don't know how to treat that yet. But I can tell you this, that the foundation, the classical foundation for that treatment to go to quantum kinetics from classical kinetics is the Boltzmann equation. So eventually we have to move away from the moments approach and get toward a full kinetics approach. Yeah.
What exactly are the initial conditions for these simulations?
So fortunately, we don't have to produce them. So, this is a family affair. So there are several stellar evolution groups in the world. So Marco Limongi and company in Rome, and we have Alex Hager and company in Monash, and there's the Mesa team, and Michigan State and other places. So they evolved massive stars in spherical symmetry. So they're realistic, in this, to the extent that spherical symmetry were correct in nature. Now we know from people who have done 3D stellar modeling for particular phases of stellar evolution that it's unlikely, the 1D models fall short in well-defined ways. So if I have a spherical progenitor, and if I, for example, perturb that progenitor, say informed by 3D modeling, if I take it and I perturb it, then I have these structures within the progenitor. It's been demonstrated that if you have structures within the progenitor that break spherical symmetry, that they will enhance the growth of the instabilities, convection and the SASE, that aid in this in the neutrino shock reheating. So you will develop them more rapidly, and when they do develop, they'll be more rigorous. And so people have actually demonstrated, just as a relative comparison, where they had a spherical progenitor and had a perturbed progenitor and didn't get an explosion in this case and did in this case. And that just kind of indicates really my overall theme, is that at the end of the day, if we want to really know whether a progenitor will explode or not and what the outcomes will be, we've got to get better at this to be able to get to that level of sophistication. Right now we have the 10,000 foot view. We've got plenty of explosions published in the literature, and it's not that they're not useful. I mean, they explosion energies and other characteristics, other outcomes have compared well. But again, there's more to be done. We have to get to a higher level of prediction than that.